Okay, let's unpack this. Today, we're diving into a research paper that throws a really interesting curveball into human motion prediction.
Oh, yeah. What's the twist?
It's about predicting motion when someone gets, like, hit by something unexpected, a physical push or bump.
Right. Usually we're talking about planned stuff, predicting someone walking or reaching for something. You look at past motion, predict the future, standard stuff.
Exactly. Anticipating intent.
Mm.
But this paper, totally different. It's predicting motion under unexpected physical perturbation.
So like getting shoved in a crowd or losing your balance suddenly.
Yeah, exactly that. And not just how one person reacts.
Okay, so how it spreads.
Right, how that impact can, ripple through a whole group of people, especially if they're packed close together.
It's the cascade effect then. People trying to recover, bumping into others?
It's predicting that purely reactive, unplanned motion and how it propagates, a huge step away from forecasting deliberate actions.
And why is this specific kind of chaotic scenario so important?
Well, the applications are actually pretty significant. Think biomechanics, understanding how we recover balance.
Okay. Yeah.
Character animation, making virtual characters react realistically.
Makes sense.
And, maybe most critically, crowd dynamics. Predicting how impact spread could be vital for, preventing dangerous situations like crowd crushes.
Wow, okay. And robotics too, I guess.
Yeah.
Humanoids reacting to bumps.
Precisely. So our mission for this deep dive is to really get into this paper, understand the unique challenges of this task,
Predicting the unexpected.
and explore the novel method they came up with to tackle it. Let's pull out the key insights.
All right, so where do we start? The challenges seem pretty obvious, but let's break them down.
Yeah, it gets really tough. When that unexpected force hits, movement instantly shifts. It's not controlled anymore. It's purely reactive.
Less smooth, right? Maybe less coordinated in the usual sense.
Totally. The body's just scrambling to stabilize.
And in a group, like you said, especially a dense one, that reaction doesn't happen in a vacuum.
No way. Someone tries to catch their balance, they might push their neighbor.
Which transfers the energy, forces the next person to react. A chain reaction.
Especially if there's nowhere to step, nowhere to go.
But you mentioned data earlier. That sounds like the biggest headache.
Oh, absolutely. The single biggest hurdle is extreme data scarcity. It's just incredibly rare to have good full-body motion capture of people getting hit by specific unexpected impacts.
Let alone getting detailed measurements during that, like the forces between people.
Exactly. Forget about it. And that's why deep learning methods, which usually dominate motion prediction, struggle here. They need tons of data and the right kind of data.
And that data problem, it's precisely why the existing methods just don't cut it for this kind of prediction.
Yeah, let's touch on those older approaches first. You had, physics-based models.
Right, simulating simplified bodies, using optimization or controllers to figure out balance recovery.
But they simulated recovery based on physics principles. They didn't learn from real human data, did they?
Nope. They couldn't predict how a specific person would react, just how an idealized model might. Then you had data-driven stuff, regression, reinforcement learning.
Those could generate more human-like reactions, maybe.
Yeah, generate, but not predict. They weren't built to forecast what someone would do next after seeing them get bumped.
Right. Synthesize versus forecast, big difference. So even the state-of-the-art deep learning models.
They mostly fail because the training data is just wrong for this.
Yeah.
Like you said, it's usually single people, moving intentionally, no external forces.
Or if it's multi-person, it's planned interaction, like dancing together, not reacting to a sudden push.
And definitely not measuring interperson forces. Plus, these standard models, they don't really have physics baked in, do they? They don't explicitly model how forces propagate.
No, not usually. Forecasting methods are mostly single person, or if they handle groups, they don't deal with this specific perturbation problem.
And the generation or synthesis methods, they might create reactions, but they aren't really built to model those close physical interactions that happen because of the push.
Plus, they might need complex simulations or tons of control signals, which makes them hard to scale up, especially for groups.
So, yeah, big data problem, existing methods fall short. They needed something totally new.
Which brings us to their solution, the Latent Differential Physics model, LDP.
LDP, okay. What were the main goals with this one?
They needed it to be super data efficient because of the scarcity problem.
Makes sense.
It had to generalize well, perform accurately beyond just the few examples it trained on.
For sure.
And critically, it needed to model those complex physical interactions within groups, learn from tiny samples, predict well in similar cases, and generate plausible motion even in totally new situations.
That's a tall order with limited data. How'd they approach it?
The core idea is pretty neat. They lean heavily on differentiable physics DP as a strong inductive bias.
Inductive bias.
Huh.
Like giving the model some prior knowledge, a head start.
Exactly. Baking in some basic physics rules so it doesn't have to learn everything from scratch. Helps it learn way more efficiently from sparse data.
Okay, so differentiable physics. But simulating a full human body differentiably sounds computationally insane.
Right, it would be. So they didn't do that. They chose a much simpler DP model. The inverted pendulum model, or IPM.
Ah, the IPM, like a stick balancing on a cart.
Pretty much. It's scalable, much lighter computationally, and it captures the essential dynamics of losing and regaining balance really well.
Which is key for reacting to a push. They felt it had the right level of granularity, you said.
Yeah, simple enough to work with, but complex enough to model the core physics, especially the interaction.
And the latent part of LDP.
That's important. They don't model the full body physics directly. They reduce the complex body down to this simpler IPM, but it happens in a latent space.
Okay, but is that reduction just some black box thing the network figures out?
No, and that's key. It's an explicit, physically meaningful mapping. They define how the body maps to the IPM.
How does that work?
So the IPM state is just the cart's position x, y, and the rod's tilt angles here. They map the person's hip joint to the mass on top of the rod and the midpoint between their ankles to the cart center.
Ah, okay. So body position directly defines the IPM state.
Exactly. And the whole LDP model pipeline, if you look at figure 1 in the paper, it goes like this. Input a full body pose frame.
Map it to the IPM state using that explicit mapping.
Then use the differentiable IPM component to simulate that IPM state forward one step in time.
And finally, use a skeleton restoration model to map that predicted IPM state back to a full body pose.
And that differentiable IPM part, that's where the physics learning happens, the forces.
Exactly. It learns the balance recovery forces, ground friction, and crucially, those interaction forces between people. The skeleton restoration model then just has to reconstruct the pose, guided by the IPM's physically plausible prediction.
Okay, let's dig into that differentiable IPM a bit more. Single person first. How does it simulate the motion?
It calculates a net force, F net, acting on that simplified IPM. For one person, it's F self plus FT plus finput.
F self is the person's own balance recovery effort. FT is ground friction. Finput is the external push.
Got it. Tell me about F self.
F self is actually two parts. There's F self PD, which uses standard PD control, proportional derivative control.
Like a basic reflex.
Yeah, exactly. It represents the general strategy humans use. Try to get back upright, stop moving unnecessarily, a default recovery tendency.
But people react differently, right? Not everyone has the same reflex.
Precisely. So they add F self N. This is a torque correction learned by an LSTM network.
An LSTM. Good for sequences, like motion over time.
Right. It learns to mimic the variations and nuances seen in the actual human motion data, adding that person-specific detail on top of the basic PD reflex. Okay, so F self PD is the physics space. F self N learns the human variation from data. What about FT, the ground friction?
They model that explicitly as damping in the IPM. It's controlled by a parameter the model learns, and it mostly affects the cart's motion, the feet on the ground. You need friction to push off and recover.
Makes sense. And they also model the broad length, changing slightly, ULT.
Yeah, because the distance between hips and ankles isn't perfectly fixed when you react. High step, bend your knees.
No.
So a simple MLP network predicts this small change based on the current IPM state. Adds a bit more realism to the mapping.
Got it. So the differentiable IPM takes the current state, calculates these forces, figures the length change, simulates forward, and predicts the next IPM state. Simple, but powerful.
Exactly. Now add more people, and you get that extra layer, interaction propagation.
This is where the differentiable interaction model, the DIM, comes in.
Correct. The DIM learns those interaction forces between IPMs, but crucially, it learns them as latent variables in that reduced IPM space.
Ah, so it keeps things scalable, not trying to model full body contacts everywhere.
Right. So the net force calculation now adds finta. Finta, F self plus finta plus FT plus finput. And importantly, all these learned forces, F self, finta, FT, are shared across all individuals.
Shared. Why is that important?
It helps the model generalize to different numbers of people in the group.
Yeah.
It learns the principle of interaction, not just specific interactions for, say, a three-person group.
Clever. Okay, so finta, the interaction force, how's that modeled?
It acts between any two IPMs that are close enough. And again, it's two parts.
Fintabebs and fintan, I'm guessing.
You got it. Fintabes is like a fundamental repulsive tendency. Think basic physics. Two things can't be in the same place.
Okay.
For the Itzwai-Karp position, it's a repulsive force derived from a potential energy function, basically, pushing them apart if they get too close, considering their positions and velocities.
And for the body lean, the Kurt angles.
Also repulsive, but the direction depends on how they are leaning relative to each other. They actually consider 9 different relative angle states, like are they leaning towards each other, away one left, one right, etc.
So fintabebs is that core, get out of my space and don't lean into me, like that's physics.
Pretty much. And fintanen, the other part. That's another MLP network.
Yeah.
Learning the variations on that basic repulsion.
Capturing the subtler ways people push off each other.
Exactly. Based on their detailed relative positions, velocities, angles. It fine-tunes the basic physical repulsion with learned human-like nuances.
So the DIM gives this physically grounded yet learnable model of interactions all within that efficient IPM space. Very neat.
And once you have that predicted next IPM state, including interactions, you need to get back to the full body pose.
The skeleton restoration model, they split this into lower body and the upper body. Right. Why?
2 main reasons. First, the IPM state, the Karp position and rod angle is naturally much more correlated with the lower body, the hips and legs.
Yeah, the mapping is direct.
Second, lower and upper body dynamics are somewhat independent. You can swing your arms differently without changing your basic walking or stepping pattern much.
Okay, makes sense. The IPM gives strong clues for the legs, less so for the arms. So how do they restore the lower body?
They use a CVA, a conditional variational autoencoder, CVAE lower.
Right, a generative model.
Yeah, it learns to generate realistic lower body poses, but conditioned on the current lower body pose and, importantly, the predicted IPM state from the physics simulation. Then a helper network, the lower sampler, picks a likely next pose from what the CVAE learned.
And the upper body follows.
Yep. Another CVAE upper, learns upper body poses. It's conditioned on the current upper body pose and the predicted lower body pose that was just generated by CVAE lower.
Ah, so the predicted lower body guides the upper body prediction.
Exactly. An upper sampler network then generates the final upper body frame.
So even though it's using neural networks for restoration, the strong guidance from the physically based IPM prediction means it doesn't need a ton of data either.
That's the idea. The physics part does the heavy lifting for the core motion prediction. The restoration part fills in the details, guided by the physics. They also mentioned using extra loss terms during training, like penalizing foot sliding or errors in the IPM state prediction and pre-training parts of the model.
Okay, it's a really elegant architecture, blending physics and learning like that, but the proof is in the pudding. How did it actually perform?
Right, the experiments. They used the FCJ push dataset, and we have to keep emphasizing how unique and small this dataset is.
The only public one for this specific problem, you said?
Currently, yes. And it's tiny, 45 single-person, 63 multi-person motions. That's it. Compare that to standard motion datasets. It's minuscule.
Wow. How was it collected?
Standing people, individuals or small groups up to 5, getting pushed by a weighted punching bag. They got skeleton data, force data for the initial push, but no data on the forces between people.
Nope, not at all. So minimal data, but highly relevant. Okay, tiny specific data set. What metrics did they track?
Standard ones, adapted, MPJPE for joint position error, hip AD and hip ABE for hip tracking accuracy, and then MBLE mean bone length error and FSE foot skating error to check if the predicted motion looked realistic and physically plausible.
And the results. They compared LDP against 11 other methods, right? State-of-the-art from forecasting generation.
Yeah, adapted baselines. And the quantitative results, looking at Table 1 and Figure 3 in the paper, were pretty clear. LDP beat all the baselines on most metrics.
In both single and multi-person tests.
Yep. And here's the kicker. It did this while needing minimal input info compared to many baselines. Some needed extra stuff, like contact labels, which LDP didn't.
Less input, better results.
Yeah.
That physics bias really seems to pay off.
Hugely, especially in the multi-person case, which is the really hard part. The improvement was massive, up to 70% better accuracy on some metrics like bone length error and foot skating compared to the best baseline.
Wow, 70%. And how did it handle stronger pushes? Did it break down?
Figure 3 shows it was consistently better, and crucially, its error increased much slower than the baselines as the push got stronger. Suggests much better robustness, better generalization.
And the baselines just couldn't handle the interactions.
That's what the paper suggests. They often failed to predict when interactions would start or stop, probably because they were just trying to pattern match from limited data. LDP, modeling it physically, did much better.
Did the ablation study confirm the LDP components were necessary?
Absolutely. Table 2 shows taking out either the differentiable IPM or the lower-upper restoration split significantly hurt performance. And the IPM guidance was especially critical for making that lower-upper split work well.
Okay, and the data efficiency. Did they test training on even less data?
Yes, and this is maybe the most impressive part. Tables 4 and 6 show LDP trained on only 25% of that already tiny FCJ dataset.
Only 25%.
Still outperformed most of the baselines trained on the full 100% dataset.
That's incredible. It really shows the power of having that physics model built in. It learns the rules faster.
Exactly. Needs fewer examples to get the hang of it. They even compared briefly to full-body physics models in Table 3.
And LDP still did better.
Yep. Supports their idea that the IPM's simpler granularity is actually better suited for learning interactions efficiently under these data-scarce conditions compared to wrestling with complex full-body contact physics.
Okay, the numbers look great. The motion is visual. How did the actual predictions look?
The qualitative results, the videos and figures, like 4, 5, 7, 11, are really telling. LDP's predictions look, well, the most like the real thing.
What about the baselines? What went wrong there?
All sorts of common issues. Unnatural poses, limbs stretching or shrinking, jittery movement, feet sliding through the floor.
The dreaded foot skate.
Exactly. Or people intersecting, or just not reacting strongly enough or realistically to the push. LDP avoided most of that.
And you mentioned explainability earlier.
Yeah, this is super cool. Figure 5 bottom. Because the IPM learns explicit forces like F-self and finta, you can visualize those learned forces acting on the simplified models.
So you can see why the model predicted a certain step or lean.
Kind of, yeah.
Yeah.
It gives a plausible physical reason. You can see the push force coming in, see the person generate a recovery force, see the interaction force push against a neighbor. It clearly shows the propagation effect.
That's huge. It's not just a black box spitting out coordinates. It gives some physical insight.
Exactly. But maybe the most striking thing was the generalization.
Going beyond the training data.
Way beyond. They tested it on stuff it never saw during training, like extra strong pushes.
How did it handle that?
Figure 9 shows it predicting bigger, more appropriate reactive steps, more body stiffening, plausible reactions to a harder impact.
What about multiple pushes? Or pushes with different timing?
Yep, Figure 10 shows it adapting. If a push stops or changes, the predicted motion changes accordingly over time. It wasn't just playing back a fixed reaction.
Okay, that's good robustness. But the really crazy part was generalizing to group size and formation.
Totally. This blew me away. The training data only had groups up to 5 people in simple setups. They tested LDP on a 13-person diamond formation, Figure 6.
13 people from training on 5 max.
And a 10-person line formation, Figure 13. Completely novel sizes and arrangements.
And it worked.
It generated plausible motion for the entire group. In that long line example, you could visually see the push propagating down the line, person to person.
Like dominoes.
Kind of. And it even looked like the push intensified as it went down the line, which is something observed in real dense crowds sometimes.
Wow. Predicting that for 10 people, having only seen small groups, that really suggests it learned the principles of interaction, not just specific patterns.
It strongly suggests those learned forces, fintalbs and finton, captured something fundamental about how bodies push off each other, regardless of the exact setup. They even think the learned friction might let it generalize to different ground surfaces, too.
Okay, this has been a really fascinating deep dive. We've looked at predicting something inherently unpredictable human reactions to unexpected impacts.
Yeah, a crucial but really underexplored area. How impacts ripple through individuals and groups.
And this paper's LDP model offers a really clever solution, blending deep learning with just the right amount of differentiable physics, the IPM.
Which let it tackle those huge challenges. The massive data scarcity, the complexity of modeling interactions.
And while, yeah, it's not a pure black box deep learning model because of the explicit physics,
that seems to be its strength. That's what gives it the data efficiency, the amazing generalization, and even that explainability by visualizing the learned forces, which you kind of need for this problem.
Absolutely. And they point towards future work, too, like maybe using more general physics models or applying similar ideas to active interactions, not just these reactive ones.
Yeah, it seems like the core LDP concept has a lot of potential beyond just this specific scenario.
So for you listening, here's something to think about. What does it mean if we can get really good at predicting how a sudden, physical shockwave travels through a group, not just the first person hit, but everyone connected.
Yeah, how could that knowledge change things?
How might it change how we design safer public spaces? Or develop smarter emergency protocols for crowds? Or even, how we program virtual characters in games or simulations to feel more physically present and react more empathetically to each other? What are the ripple effects of predicting the ripple effect?